So there's a trivial proof. So a trivial proof usually is something that kind of follows more or less straightforwardly from known results, which have sort of, yeah, I would say. Um, Something that doesn't really take a very long chain of deductions, perhaps, to prove. So what might an example of this be? And also, I will say that a proof being trivial really is a relative phenomenon. So, for example, if you're a math student, you might be asked to, for example, prove that the sum of two odd integers is an even integer. But for at a certain point, this fact is a trivial fact. Like it really is not difficult to prove, and it would be a waste of the audience's crowd. The audience's time. I don't know what's wrong with me today. I do, but the audience's time. It'd be a waste of the audience's time to actually go through the steps to show. And so you can say like, yeah. I mean, you would hope that when an author uses the phrase, "the proof is trivial," that what they mean is perhaps it follows only a few inferential steps. It's only a few inferential steps away, like maybe one or two inferential steps away from like some already listed result, some already described result, or maybe definition. So like definition, a rectangle is a four-sided figure where each of the angles is a right angle. Definition, a square is a four-sided figure with equal length sides and right angles at every vertex or whatever. Claim, a square is a rectangle. Proof, the proof is trivial. I'm doing great, Cootie Juice 69. I got beans in the fridge, but probably need to make a new batch. Listen, it's not an official designation, okay? This idea of being a trivial proof. Probably if in the judgment of your peer reviewers, the proof is not trivial, then you will be asked to supply the details. Yeah. We should look through books and try to figure out where they actually say this phrase, the proof is trivial, to see whether or not it feels that way. Or, I mean, like it's a meme, I know, that in books, it's very often the case that what's trivial to the author, for example, can require hours and hours of your time to try to figure out. So it really depends on the audience. Yeah. Good night, QSD. I hope drink lots of water. Okay, drink lots of water, so you aren't feeling too devastated tomorrow. See you later, QST. Love you. Ooh, you should check out Robert Wyatt. Have you heard Robert Wyatt? Rock Bottom's a pretty cool album. No, he was in Soft Machine. He was the drummer in Soft Machine. And I think the story goes that he had to quit the band because he got thrown out of a window and ended up paralyzed from like the waist down. Something like that. If you raise a multiple of 3, if you square a multiple of 3, then add the digits recursively until you get a single digit. That digit will always be 9. Yeah, it's pretty cool. I might not be getting the details of his life. Right. Too big to flail. Hello. But yeah, Robert Wyatt's Rock Bottom record is pretty cool. So Hennestein, do you think you could prove that? Well, so let me give you a hint. That property of that digit sum property is really going to be a property of any number which is divisible by 9, except for maybe 0. I mean, 0 is strictly speaking a counterexample to your claim. But if you take any number which is divisible by 9, add up the digits, and you do it over and over and over again, you will end up with something equal to 9. So really, the game is to show that something which is divisible by 9 has that property. Well, then you do it again. 9 plus 9 equals 18. But what's 1 plus 8? Sure, you can think of it as adding until a single digit, yeah. So the claim would be, the claim that I think you can try to prove if you want to, is that if n is divisible by 9, then the digit sum will also be divisible by 9. And if you keep doing this digit sum if you keep doing this digit sum over and over again, then eventually you'll hit 9. So it's really good if you know modular arithmetic. Knowing modular arithmetic would be very helpful in attacking this problem. Because what you want to do is think about how to access the digit sum of a number and take that digit sum and look at it mod 9. Oh, and it's important, by the way, the digit sum here is in base 10 of n in base 10. It's critical that it be in. Yeah, it's a very common. It's a commonly taught trick to test a number for 9. But yeah, there is a proof of it that you can use, that you can do, to show that it always works. We can talk about it if you like, or if you want to sniff it out yourself, you might try. Yeah, I actually don't know the 7 trick myself, but I remember there's an 11 trick where you take the alternating sum of digits. That follows from modular arithmetic as well. Not quite sure about the 7 trick. Can I mention a little bit of the concept of limit, especially left and right hand side limit? Okay, sure. So, oh, you couldn't see any. You couldn't see it in my gameplay. Oh, sorry. Really not together today. Yeah. So let's say we have a function which looks like this, or actually, we can be very explicit about it. All right. let's let f of x be a function which is piecewise defined. So let's let f of x, for example, equal x if x is less than or equal to 1. And let's let it be equal to, I don't know, 1/2 x plus 1/2 x plus 1 if x is greater than 1. Just making stuff up here. Then let's try graphing this function. So here's maybe x equal to 1. But up until x equal to 1, we know what the graph of this function looks like. It looks like the line y equals x, which is very easy to draw. It's this line right here. And then, so this y value here is 1, by the way. And then at x equal to 1, of course, there is a break in the definition. And for x greater than 1, the function looks like 1/2 x plus 1. So that's a line of slope 1/2. And let's see, at 1, if we were to evaluate this expression at 1, we would get what? 3/2? So 3/2 is maybe like right here. And then we keep going up, but we go up with a slope not of 1, but of 1/2. So we're going to have something that looks like this, maybe. Okay? So here's a function. And here's what I want to say about it. What is the limit as x goes to 1 of f of x? Well, let's think about one-sided limits, actually. So what I want to do to really make this apparent is let's take the limit as x goes to 1 from the negative side. We denote that like this. So we're going to restrict our attention to those values of x approaching 1 that are getting closer and closer to the 1, but from the left side, from the negative side. So Slap Nippy, could you tell me what you believe the value of this one-sided limit here? Could you tell me what you think that the value of this one-sided limit is? And while you're at it, you might think about what is the limit as x goes to 1 from the positive side of f of x. Good. So this is 1. Absolutely correct. And the reason is because as x gets closer and closer to 1, from the negative side, from the left side, f of x is getting closer and closer to the y coordinate of this red dot here, which is 1. And if we have the limit as x goes to 1 from the positive side, what is the value of f of x? And remember, maybe I'm giving it away, this point right here is 3/2. So actually, I won't even bother you about this. If you think about the limit as x goes to 1 from the positive side, f of x is getting closer and closer to 3/2. Now, the fact that the left and the right limits, the fact that the left hand and right hand limits are different from one another, we can clearly see they are different, implies, these two facts imply that if we write down the vanilla limit, this one here, what can we say about this? The only thing that we can say is that it fails to exist. It does not exist. The only way that it could exist is if both one-sided limits exist and are equal to each other. But the fact is, the one-sided limits of this guy, they do exist. However, they are not equal to each other. So the limit overall, the two-sided limit, if you like, of this function fails to exist.
On the planet with liquid hot magma.
Wow, thank you, Time Traveler, for the subscription. That's really nice of you. Oh, it's a slow day today. Not a lot of math questions today. Kind of surprised, but maybe it's Halloween, so who people are out having a good time. As well, they should. I'm scared of GitHub. I have a deep fear of GitHub. I think it's a justified fear. Because, okay, this is what happens. I go to GitHub and it's like all these files and they're just available for me to get. I can go get them. I get them. I'm following the directions in the README file. And then, like, one of the things that it asked me to run, it's like I download a .jar file. And I have no idea what the .jar file is going to do when I open it up. In fact, Chrome is warning me in no uncertain terms. It can be dangerous to run this type of file. And I'm like, oh, right. Because it could do like anything it wants to do to me. Am I just going to accept that willingly? This is my fear. Now you might ask, well, do you ever download any software from the internet? And of course I do. Of course I do. But my thing is that there's a large community of people that are studying, for example, the various elements of the software that are in like the Linux repositories, for example. And Linux itself, somebody brought this up. Do you trust Linux? Because you probably haven't read through the source code of that, and certainly I haven't. But yeah, I do trust it. Because there's so many people working on these things that if somebody was doing something super nefarious, I feel like this would get caught. Now, I don't know for sure. Maybe there is some like bad stuff happening on my computer as we speak. Don't know. But a random .jar file, I'm not sure that it meets that level of scrutiny for me. So that's my fear. Right. So then it becomes a calculus of, am I actually going, is it worthwhile for me to open up the source and look at it? Because, like, for example, what are the things that I could use GitHub for? One of the things was for a Twitch queue bot, a queue for Twitch chat. And, you know, it's cool that somebody made that. It's very cool, but I didn't want I'm not really an expert at reading code to begin with. Like, I wouldn't know what much of the stuff in there is doing. Yeah. You can use GitHub for sharing notes. Yeah, that's cool. See, I know that there are those kinds of uses for GitHub. I think it's very cool, but I just get scared because I am a fear-based creature. What can I say? I'm a fear-based creature. Of a virus? I don't know if it's that. I just like, can't programs do nasty things to my computer if it wants to? I mean, like a virus, sure, is a program that can do nasty things. And I just don't know that these pieces of software are good or bad in that regard, or fine in that regard. Just don't know. GitHub is just a platform. I think you meant that you don't trust. Sure. That is what I meant. But like, it's hard for me to know or understand how vetted by the community any particular project on GitHub is. I understand the definition of relative homology, but my notes don't mention any geometric interpretation of it. In relative homology, right, you look at the homology of a chain complex where the chain groups are like Cn of x modulo Cn of A, where A is some kind of subset. And maybe you denote this Cn of x comma A or something. So what you're kind of doing is you're kind of ignoring any of the topological features that might be living in A. And in particular, if you have a chain whose boundary is in A, then you think of that as being a cycle. It's kind of like, maybe one way of thinking of it, I'm not sure if this is a great way of thinking about it, is to think about perhaps the space x mod A, where you sort of take A and crush it down to a point, the quotient topology. And perhaps think about homology groups there. I think that there might be some technical issues in thinking of it always in that way. Yeah, so if we open up Hatcher here, let's take a look at good old Hatcher. There's my copy of Hatcher. I'm proud of it. I like it. Yeah, this is an old copy. I took the class, it says here, fall of 2000. And it was still when it was only available in a PDF form. And we had to go to a copy shop to pick up this paper-bound copy. But I gotta say, the binding on this is exceptional for being, you know, it's a paperback thing. This is not thick stock or anything like that, but somehow the binding is really excellent. No pages have fallen out of this book, so they did a really good job. There is, oh, I just said that, but then I guess there's this one, so never mind. But no, it's pretty good, pretty damn good for being nearly 20 years old now. So maybe this proposition here is helpful. So for all good pairs x comma A, you can look at the quotient map of this pair, and this induces isomorphisms between not homology, but rather not the homology of X and A, but rather the reduced homology. So there's definitely, it's really not a big deal. It's just what you get by adjoining the usual chain complex with at C0. After C0, you attach an additional map, which goes to just Z. Basically, what it does is make H0 be, or H0 tilde, the reduced homology, be 0 if it's a connected topological space. So it doesn't, strictly speaking, count connected components anymore. But there are a number of like technical reasons why it's useful to have, I guess, and this being one of them, why it's useful to have reduced homology around. But the basic idea is that as long as you have a good pair, then you have isomorphism between hn and hn tilde. Yeah. N greater than equal to 1, in fact. So basically, just think of it as the quotient topology. A tank full of water has the shape of a paraboloid of revolution. That is, its shape is obtained by rotating a parabola about a vertical axis. If its height is 4 feet and the radius at the top is 4 feet, find the work required to pump the water out of the tank. After 4,000 feet-pound of work have been done, what is the depth of the remaining in the tank, of the water remaining in the tank? So there's some kind of parabola. There's some parabola which has the property that, I guess, when we rotate it around the y-axis, for example, we get a tank whose height is 4 feet and whose radius is 4 feet. So like if we made y equal 1/2 x squared, maybe. Then let's see, if we put in x equal to 4, ooh, that's too big. So we need 1/4. 1/4 x squared. So if we put in 4 here, it's like I'm guessing what the book wants you to do, which is unfortunate. Yeah. Well, anyway, so we have, I think this is an equation for a parabola which looks like this. And if we were to revolve this parabola around the x-axis, I don't know what I'm doing. If we were to revolve this around the x-axis, we would get that that tank. Right? All right. So I guess what we're going to have is a situation where we've got the water filled all the way up to the top. And we're going to be draining it. Is that right? So then we're going to be calculating the amount of work required to drain this thing from its initial height, which is 4 feet, down to some height, call it h. We want to compute the work required to do that. So what we're going to compute is the amount of work required to get the water that's in this tank that goes down to a depth of h, the work required to pump that through the top of this tank. Every layer requires a different amount of work, so we use an integral. Exactly right. That's exactly right. So I guess the thing to imagine, yeah, no, you got it. Every layer requires a different amount of work. So what we want to do is calculate maybe dW. dW is the amount of work required to pull out an infinitesimal slab of water located at some height, which we could call, well, let's call this height here, this height, well, we can call it h, it's fine. So this is the work required to pull out, to pump out a slab of water of height, let's call it dH, located at h. Does this make sense? So we're going to be looking at an infinitesimally thin slab here of height dH, or we could even call it dy if we wanted to. That might be more evocative. Yeah, dy. Maybe that's more evocative and better. So we got to figure out the work required. Now work is force times distance, right? The force is of course going to be the weight of the water, right? So this is going to be equal to the weight of the water multiplied by the distance we pump it out. Now the distance that we're going to be pumping it out is 4 minus h. Does that make sense? The weight of the water we can further break down, because that's going to be the volume of water multiplied by the density of water. And I have no idea what the density of water is in cubic feet or whatever, like pounds per cubic feet. I have no idea. But this is going to be the volume of water multiplied by the density of water multiplied by 4 minus h. Oh, times g. I'm sorry, times g. We need the gravitational constant as well. So just to make sure that we are operating in a sane fashion, let's just compute the units on this. I'll explain 4 minus h just a sec. So the volume of water is cubic feet. The density would be cubic feet per, no, pounds per cubic foot rather. Pounds per cubic foot. 4 minus h is feet. And g is feet per second squared. So 4 minus h is the height, the distance that we are pulling the slab of water out. We're pumping the slab of water through a distance of 4 minus h feet. We're not using SI units. We're in America. Really, yeah, feet per fortnight squared, really. That's really what these should be, but does that make sense, Face? Yeah. And then what you're going to want to do is integrate. Sure. American units. No problem. Your wish is my command. No, fuck no. Are you kidding? Okay, first of all, there's two things that are abominable about what you've written. The first is that crazy pointing in the wrong direction hard bracket. Oh, I guess you're saying you like the roundy bracket. Well, good for you. Anybody that does it the other way around, if you find yourself ever in your life writing this, please ask yourself what you are doing with your life. But yeah, that's the other bit. Semicolon? The semicolon hurts in irk. The semicolon hurts. This, though, it's hard for me to go too hard on this thing. It's very difficult for me to overstate how hideous this looks. I heard French people do it. Just saying. I mean, no commentary. That's just what I heard, okay? These are just facts. I respect. I like it. I appreciate the oppositional defiance. I like it. But this is ugly as fuck, holy God. No, the way this should be written, people, is like this. This is very evocative. I refuse to ever do this in my life. I will never. I mean, I've done it here for demonstration purposes, but no, I didn't know. Not even a little. Nope. Not even a little. Not even a little. I know it looks like a point, but listen, if you are reading something and you can't tell whether this is a point or an interval, we've got bigger problems. Okay, we need to talk. It should always be clear from context whether this is a point or an interval or what. I mean, this is like demonic looking. Look at these look like the wings of some kind of frightening monster. It scares me. It's like gonna come and attack me. This feels very threatening. I think also, you know what these things here evoke? Staples. They look like staples. Staples are sharp. They're ready to hurt you. You don't want a staple in your eyeball, for example. Yeah, there's a lot to fear here. Many emotional connotations with that notation that I don't want my readers to have to take on the burden of. It's unethical and it's wrong. You should not do it. Unethical. You love a staple in your eyeball. Okay, well then, this is the notation for you. So, W, I apologize. W is going to be the integral of dw. Right? Where you're going to integrate from something to something. And I would say that you could integrate from h to 4. Should be fine. So, are you at a loss for how to evaluate or to compute this dw guy? We can talk about it. Density is just some constant. I don't know what it is. There's some density of water. Water has some number of pounds per cubic foot. No clue what it is. You can look it up on the internet, I'm sure. So density is just some constant. G is just some constant. I don't remember what it is for feet per second squared. I don't remember. Yeah. The volume. Well, this is something that you want to think about. Okay. So the volume of water. So if we think about it, the radius of this, we want to figure out the radius of this slab of water. We want to multiply that by, we want to square it, multiply it by pi r squared, and then multiply that by dy. So I guess our job is to figure out first, what is this radius here. Oh, and because, yeah, this is a little confused, isn't it? Because I put dy here, I should probably be calling this y instead of h. Can I do that? Oh, that changes a lot of things. Let's call it dh instead. dh instead. Let's call it dh instead. So, oh, this is all very confusing, isn't it? Because I'm using h in multiple places. We're going to call this lower bound of integration here, we're going to call that h naught. Okay? This is very confusing. Okay, so let's just go back. The work required to pump out a slab of water of height dh at h. So it's got a depth of h, all right? And we're going to be pumping out this slab whose thickness is dh, is infinitesimally small. Oh, so I thought that what we were doing in the original problem was just pumping out water to some specified depth, so that there was some water still left in the tank. So we were going to pump out the water, which goes from h equal to 4 down to h equal to h naught. This is what I thought we were doing. H naught may be down here somewhere. And then I thought we were going to set that equal to 4,000 and then solve for h naught. Oh. Yeah, that's a good point. Okay, Carbon, that's a good point. Maybe we shouldn't have G in here, because what we really want in the end is for things to be measured in pound feet. So I guess that the force is already sort of bound up in the density. Like, really, density should be mass density. It could be mass density or weight density, I guess. But I guess as I've written it, this is going to be measured in weight density. So maybe we don't need G. That's a good point. Thanks. So let's just get rid of the G. Anyway, so what is the volume of water at height h with thickness dh? What is the volume of that slab? Well, what we need to do is figure out the radius of that slab. Right? Now, what we can do is use this equation, right? If we forget about y here, what if we called this instead h? H is equal to 1/4 x squared. If we know that the slab is at height h, we can figure out what the radius is by taking this equation and solving for x, right? The positive value of x in this equation will represent the radius of this slab of water. So if we solve, we get 4h is equal to x squared. So x is equal to plus or minus the square root, or 2 times the square root of h. Now, of course, we're going to take the positive branch of the square root. The other branch is this value of x. But the radius of this slab of water is 2 times the square root of h. So then what is the volume of water? Well, it's 2 times the square root of h, that whole thing squared, multiplied by, so that's r squared, multiplied by pi. So that's the sort of area of the circular disk of radius 2 square root of h. And then we're going to multiply this by dh, the thickness of the slab. The density is just some number that I don't know. We can call it rho. You can look it up on the internet. And this thing is 4 minus h. And then what you need to do is integrate this from h naught to 4, this quantity here. So pi, if we square this out, we get 4h times rho. A lot of these are just constants. Times 4 minus h times dh. I think this is the integral that you want to do. So that's the work required to pump all of the water down to a depth of h naught. And then you want to set that equal to 4,000 or whatever that number was. And then solve for h naught. And then you'll know the depth of the water left in the tank after doing 4,000 pound-foot of work. I hope that's right. Okay, so yeah, that's fine. That's fine. So there are two important numbers here. Well, three important things. First important thing to notice, that's nice about this. The first important thing to notice is that the coefficient in front of x squared is 1. Nobody writes the 1, you agree, but there is a coefficient of 1 in front of the x squared. That's a nice fact. You agree? The other two numbers that you want to pay attention to, Love Geo, are the 4 and the negative 45. What do you mean, how? Like, I could equally well write this as 1 times x squared plus 4x minus 45. But nobody's insane enough to write that 1. Nobody does that, is what I'm trying to say. We all just write x squared when we mean 1x squared. So in a situation, in a situation where the coefficient of x squared is equal to 1, hi, happy Halloween to you as well, Skugget. In a situation where the coefficient of the x squared term is 1, you can factor this thing if you can find a pair of numbers. So we want a pair of numbers P and Q, okay, so that two things are true. First thing that we want is we want P times Q to be equal to this constant term, negative 45. That's the first thing that we want. The second thing that we want is that P plus Q, the sum of P and Q, is 4. And my claim is that if you can find such numbers P and Q, you can easily factor this polynomial. The reason, and in fact, if you can find these numbers, then the polynomial factors as p x minus p times x minus q. No, wait, what? It's the, sorry, x plus p times x plus q. I know what I'm doing. Leave me alone. Now, let's make sure that we understand why. Do you understand what I've written thus far, Love Geo? I really want you to understand this because this is very important. It's going to come up a lot in your life. More than you want it to. A bit. Okay, well, just indulge me for a second and suppose that you were able to find such numbers P and Q. What I want to show you is the reason why these conditions, the reason why we need these equations to hold. The reason why is because if we expand this thing, maybe you call it something starting with an F that has 4 letters, but if we expand this thing, what we get is x squared plus xq, or q times x, plus p times x, plus pq, right? And of course, we can rewrite this as x squared plus p plus q times x plus pq. And now, look. A 4-letter word starting with F. Yes, absolutely. Look, if p plus q is 4, and p times q is negative 45, then when this thing when we expand it out, we get precisely the polynomial that we started with. This is the reason why we want these two conditions to hold. Good. So, can you find such a pair of numbers? So, here's the secret. Because I imagine that you're in like maybe a like an algebra 1 class or maybe algebra 2 class. Because of that fact, all of the answers that you're going to get almost always are going to be integers, whole numbers. That these problems will be very specially crafted in such a way that P and Q will almost always be integers. Now, this won't always be the case. At some point, things are going to get more difficult. But here at the beginning, these things are going to be integers. So let me ask you an even a simpler question. Can you find a pair of integers, P and Q, whose product is negative 45 and whose sum is 4? Yes, perfect. That's exactly right. No, you're exactly correct. 9 and negative 5. Yes, absolutely. Here, P is equal to 9 and Q is equal to negative 5 work. Because why? Because 9 times negative 5 is negative 45, and 9 plus negative 5 is 4. So, x squared plus 4x minus 45, your given quadratic factors as x plus 9 times x minus 5. And this is it. So yeah, this is what factoring means. Factoring means you take something like this and you write it as a product of things. In the same way that like when you have an integer and you factor it, you write it as a product of things. You write 6 as 2 times 3. In the same way, you're going to write this guy and write it as a product of things. In this case, x plus 9 and x minus 5. Why do you want to do that? It's a different question. It's useful for many reasons. It's useful to do. Useful to know how to do. But in any case, this is how it's done. Okay? Yeah, everything that I've said here, going from here to here, holds as long as the number in front of x squared is 1. If the number in front of the x squared is 1, then you can apply this idea. How can I find a tight bound for the sum of the square root of floor of k? Floor of square root of k. So let's just look at it real fast. Or I don't know. Do you think Desmos knows how to do this? So this is Desmos's graph of the floor of x. And we can put in here y equals the square root of x as well, right? And so one thing you might observe from this is that, sure, one thing you could do just to get an upper bound is to integrate square root of x, right? You could take the integral of square root of x from 0 to whatever. Maybe do slightly better integrating from 1 to whatever. I mean, it doesn't seem obscene to just compute it more or less straightforwardly. because these numbers are they're just going to be the areas of these rectangles, the rectangles between these red bars and the black axis. Yeah, I'm not sure what's happening in the background. I think my children are getting into the Halloween spirit. So it looks like to me, just looking at what Desmos is printing out here, that it's going to look like 3 plus 2 times 5 plus 3 times 7 plus 4 times 9 plus 5 times that. So it definitely seems doable. So it looks like something like if you want the sum from k equals 1, and I don't know why you want n squared minus 1 exactly. That's making me mad, so we're just going to go to n squared, and then you can subtract off whatever you want at the end. So then this is equal, so this is what did you want? The floor of the square root of x, square root of k, excuse me. And it looks like what this is, from what Desmos is saying, is that it looks like this is equal to 3 plus 2 times 5 plus 3 times 7 plus 5 times 9 all the way up to something times n squared. Well, sorry, n squared, I guess, minus n minus 1 squared. So n squared minus n minus 1 squared. N minus 1 squared. And we can probably figure out what that is a little bit better. N squared minus 2n plus 1, which is 2n minus 1. So this whole thing is 2n minus 1. And then we multiply that by, I believe... Oh, wait, did I mess up? 1, 2, 3... Yeah, this should be 4. I don't know why I thought it was 5. It should be 4. Because this should just increase as n does. So then we multiply this by n. So we want to find a closed form expression for the sum from k equals 1 to n squared. Oh, sorry, for the sum of 1 times 3 plus 2 times 5 plus 3 times 7 plus 4 times 9 all the way up to n times 2n minus 1. I believe that this expression here is that. Well, so this term, general term here, so another way maybe of writing this then is that this is equal to the sum from k equals 1 up to just n of k times 2k minus 1. But this is, of course, the same thing as the sum from k equals 1 to n of 2k squared minus k. But this is, of course, the same as the sum from k equals 1 to n of 2k squared minus the sum from k equals 1 to n of k. Now this one I know off the top of my head. This one I had to think hard about. But you can pull out the two, and I mean, I think it's a relatively famous formula for the sum of k squared. Does anybody remember what it is? The sum of the first n squares. It's like 2n plus 1 times n plus 1 maybe over something. Wait, am I confused? Oh, it is confusing because it's like a notch above where it should be. No, but we're in the realm of getting exacties here. We're in the realm of actually nailing it on the nose. But actually, I think it matters for what I've written down here, because if you look back at what Desmos gave us, if you look back here, what I was doing was counting the number of squares underneath these red line segments. But I think that if I include the n squared term, then I'm including one of the columns of rectangles of squares here. So in fact, I think that this argument right here, I think it actually requires that we have -1 right here. You see how I fixed it? I'm instead going from k, so ignore all this. This is all bad. I'm saying that this sum right here should be the sum from k equals 1 to n minus 1 of k times 2k plus 1. Two n minus 2 plus 1 is 2n minus 1. Does this look right now? I feel like this is right after a lot of thinking. So then this ends up being the sum from k equals 1 to n minus 1 of 2k squared plus the sum from k equals 1 to n minus 1 of k. And so this we can replace by that, where n is replaced by n minus 1. So we get 2n minus 1 times n minus 1 times n divided by 6 plus this one, which is Gaub's famous thing. N minus 1 in this case times n divided by 2. Good job, Gaub. Yeah. So then we can simplify this. Or rather, somebody can simplify this. Why does the dot product between two unit vectors give the cosine of the angle between them? Well, that is a consequence of the more general fact that the dot product of two vectors is the product of the lengths of the vectors multiplied by the cosine of the angle between those vectors. So obviously, if the lengths of the vectors are 1, then the dot product gives you just the angle information. However, you can then naturally ask, well, why is that so? Why is it the case that the dot product of two vectors is the product of their lengths multiplied by the cosine of the angle between them? And the reason for that is because of the law of cosines. The law of cosines actually generates that result for you. Yeah, so if you look at, for example, how does this work? So if you have two vectors, u and v, and you have this angle between them, theta, and you look at u minus v. So this vector right here, this vector is u minus v. Then what the law of cosine says is that the length of u minus v squared is equal to the length of u squared plus the length of v squared is it minus or is it plus? Oh, it's got to be minus. Minus 2 times the length of u times the length of v times the cosine of the angle between them. This, of course, is the, yeah, exactly. This, of course, is the dot product of these two vectors. Or sorry, the dot product of this vector with itself. These here are the dot product of u plus the dot product of v. This is just what it is. If we use the property of the dot products that we know, like bilinearity, then this becomes u dot u minus 2 times u dot v plus v dot v and then that and that will kill each other, that and that will kill each other. We can divide both sides by this quantity, negative 2 norm u norm v, and we get that u dot v divided by the norm of u times the norm of v is equal to the cosine of theta. And so if norm of u and norm of v are 1, then of course the dot product is exactly the cosine of the angle between them. What fun. I love you all. Have a great rest of your Halloween. If the festivities are not yet concluded, enjoy yourself. I hope to see you on a future stream. Take it easy, y'all. I love you. Bye.